This is not supposed to use this.
There's a few of this too, which is you just reassociate and then HH is I. You can either do that by all natures by that along we have one.
We already have that distribution.
We have that H is, we know that H
But is that in general?
is unitary. So if H is unitary, then HH, we're given that H is its own address. So you can do this with three lemmas, you can do this with all of it. This is pretty simple. In fact, that's kind of why I concluded this exercise. In principle, prove it correct. It's really each twice.
Okay.
Okay, welcome back. We're going to pick up around where we left off. We're going to be talking a bit more about qubit, multi-qubit. In particular, we want to find a way to capture the notion of measurement in a way that we can reason about it. And in order to do that, we need to create some sort of relation, right? We need to capture the ability that there are multiple possible outcomes. So we're going to make an inductive relation here called measure. It's going to take some qubit and some R in qubit. It's just going to build a relation that says, well, okay, this first qubit has this certain probability of collapsing to this state, right? So when you say measure zero, the measure zero of a qubit just kind of extracts what the chance is that it will collapse to zero. It will measure to zero. And measure one does the same thing, but for one, right? And so it's kind of like natural first problem here is, well, we can say, okay, well, we're measuring some zero state with some probability p that it comes to some other state. We know it's non-zero, the probability. The only thing it could be is the case that it is measuring to zero then, because it's already a zero, right? So just to kind of show off why we actually want to build this relation, why we use this measure relation is there's a nice tactic called inversion, which will kind of allow us to tie these things together. And so we'll get these nice equations and it says, okay, well, I know that by inverting, I know that we're building a measure. I know it has to be a measure zero or a measure one. And I know then that this last argument here, this phi, by inversion has to be a zero or it has to be a one. And you can handle each case on a case-by-case basis, right? That's just reflexivity, so we can say that's easy. And then here we have to find the contradiction. It's easiest to do if you substitute everything in. And you can see you have kind of two options. And this certainly is zero on the left-hand side. So we can do a contradiction on H3 and then non-zero. Oh.
It's just LRA or else.
LRA, yeah. Because those use non-zero and it'll do this implication beforehand.
Can you explain what line 194 means?
Well, line 194. Yeah, so line 194, it depends on this measure relation, right? Which this is saying that, okay, we have a qubit in state zero, and we want to say something about the possibility of it collapsing to a phi. We know for a fact, or measuring to a phi, we know for a fact that the probability of it measuring to whatever phi is non-zero, right? But it's a zero state. Measurement won't do anything to change it because you're measuring as the standard basis. And so that tells us that, well, okay, the only state it could possibly collapse to is actually the zero state, which is what it currently is.
So it's not measured, like if you measure the state zero, then the probability of it collapsing to phi is p. Isn't that how it's supposed to read that?
Yes. Yeah, that's how you're supposed to read that.
So why is phi, like, the probability is non-zero, it doesn't have to be equal.
Okay, so here's what's kind of happening is that there's two possibilities for what measure could be, right? It could measure to a 0 or a 1. But because it's a 0 state, we know that it has 0 probability of measuring to a 1, right?
Oh,
So that,
the measure, okay, the only constructions that are allowed is like the basis.
right.
You can't instead measure, okay.
Yeah, it's just measuring to 0 or 1. It's yeah. And so since we know that the chance is 0 here, we know it has to go to the 0 state. Right, and so you get the same kind of statements for measure 1 and measuring for plus, where you can kind of guarantee the probability for plus. And so that is the end of qubit. And we can look at multi-qubit, which is much more interesting example. Right, working with just one qubit, you can't do very much. Right, so multi-qubit, we talk about quantum states now, right, where we're going to have vectors of size 2 to the n. And then we can define the basis states and give them with a nice notation, so you can use Brockhead notation. And then we get decomposition.
I don't think it's read.
Oh, okay. Sorry. Right, so we had qubit decomposition for the single qubit case, but we can also get it for the multi-qubit case, right? We can say, okay, well, we have a quantum state with 2 qubits in it, represented here by phi, and we know that it just represents some linear equation of combinations of basis states, right? Which is what will actually allow us to reason about arbitrary states, because we know how to do computation on basis states. So, yeah, in order to approach this, actually, so at the start of this session, I have a nice solutions file for when we get stuck. So we'll hopefully get through this much quicker. But yeah, so how would we want to get started with this? Well, it's kind of the same way as before, right? We know what these should be, and I'm just going to, oh gosh, it's not in the solutions file. Well, but the general gist is we know what these should be. We can provide exactly what it is and use our automation tactics in the same way as before to solve it. Right, and so then we can actually talk about, okay, well, how do these operate? We can define the C0 in the standard way using this L2M here. It takes in lists and turns them into matrices for us. So it's a handy tool to write out a matrix in a way that's visual and then go ahead and use it. I'm going to describe how C0 operates on the basis states. Just using LMA, we can just hand it one part of the basis and then have it go over. Right, and we can talk about how actually C0 operates on different Cs as well. So you can have a plus with 0, and you'll see you get the entanglement that you would expect. Right, and so that gives us the Bell pair, and we can define that as its own object because we might have to reason about that at some point. Yeah, so we can talk about applying single qubit gates to multiple different things just using the Kronecker product. At this point, we're able to say, okay, well, we can talk about, well, we're applying an X to the first wire and an H to the second wire, and we have certain inputs, and we can measure what they would we can look at what the exact output would be as a linear system of equations. Underneath all of this, it's just going through doing these computations for us and showing, yeah, actually, yes, these are both the same linear system of equations. Everything lines up using all the LCA and LRA and LMA tactics that we've been building.
I have a question.
Yes.
You said entanglement earlier. Can you define that in more detail?
Define entanglement in more detail?
Yes.
Yeah, so apologies. Entanglement is tied to the concept of measurement. It means that when you measure one qubit in a quantum state, it locks off certain possibilities potentially for the other qubits in the quantum state. As this looks as a linear equation, what it means is really that, well, we can actually just look back at the equation itself and see, okay, well, right, these two qubits, their value is always tied together in some way, right? Where if we measure this as a 0, it means that the other qubit must be a 0. And since we can think about measurement as operating on single qubits in a quantum state and not the whole state itself, we are able to kind of have this entanglement property cause effects in the rest of the program. And so it doesn't have to be 0, 0. It could be 0 and 1, and then 1 and 0. They're still entangled even though they have the opposite value. So it's not matching values. It's the measurement of one qubit affecting the value of another.
Maybe the power of it is just that this is equal to plus plus and minus minus as well. So no matter what, I mean that's the power of entanglement. Because this could be the way you describe it could be just a mixed state.
Right. Yeah. You could just describe this as a mixed state. But when and
so you could measure this one particular.
This one in particular.
Measure in any basis.
Yeah. You can.
You get perfect correlation.
Yeah. Entanglement is kind of an independent concept of the basis, right? And for most of our reasoning, we do it in this library. We talk about the standard basis 0 and 1, but you're not restricted to that. That's what you're saying, right? Okay. Right. So we can define the Bell pair because in particular we find it might be useful. And we can then talk about gates operating on single qubit gates operating on different parts of the state using the Kronecker product. We're able to build a larger operation where this is equivalent to just an X on the first and a Hadamard on the second. And this is us applying Hadamard to both. And LMA is able to show these things are correct for us. Right, so we're able to then we can start saying, okay, well, I want to say that we've defined a Bell state as actually a circuit itself, right? So this is sort of the closest thing we have to a circuit right now, where we're composing an operation on the first qubit with a CNOT afterwards. And we can show that these actually do amount to the same thing. Anybody have any idea for what might be the first thing we attempt?
LMA.
It would be nice. Let's see. It works. Yes, the automation is fairly powerful, right? Where we can just say, okay, well, we have a couple of things being multiplied together here, but yeah, it works out to be this state for us. We have some other useful gates kind of defined. If you want to use this to maybe build a language on top of that, you can talk about verification. And these are sort of the standard things you might need, right? You'll have not C, controlled C, and swap gates. And we can actually show, well, yeah, no, they do work exactly how we would expect, right? On these multi-qubit quantum states that we have, right? Where we can use LMA, and the destruct here is just kind of destructing this X and Y, which are natural numbers, and then it builds the state from those. If it's 0, it goes to a 0 state. If it's 1, it goes to another. And then it can be solved for us automatically. Right. So,
could you prove now that 0, 0 plus 1, 1 is the same as plus, 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 minus 1?
Good question. So 0, 0.
Bell state.
The Bell state?
No,
yeah.
The Bell state is the standard basis and the plus minus basis.
Bell is equal to plus plus, right?
Plus minus.
And normalized.
Plus, oh yeah. Plus sorry, this minus, and then normalized. Do we have a, yeah, that, will I just be able to do that?
No, just add the 1 over square root of 2.
Yeah.
Yeah. Oh yes, I need to do a scale. That's what it is. Hopefully I've written that out correctly.
Are you sure?
I'm not certain.
Do we have-
Plus, I don't think it's defined as syntax.
Yeah, we don't have that as a notation.
Write the tensor explicitly.
Yeah.
Plus tensor
Okay,
plus.
then H1.
Yeah, so we'll do,
Yeah.
Yeah.
Use a tensor, you can just do plus and plus. Yeah.
just do a tensor between those and then, okay, so that checks, good. All right, and it's not able to do it automatically.
Maybe it's
Hmm?
you have to unfold that by any chance?
It worked before. I would
She
try.
did it for that.
Okay.
Yeah, I would just try, because square roots of 2 can be hard. I think
Yeah.
where we tend to use C field. So I would just do a by cell and then see if C field maybe you can handle these.
Yeah, okay, so let's we can try the full just C field and see if it works. Okay, so let's try, or let's do C field simplify, because then we can see where it's
Yeah,
able
it looks like maybe not unfold the bell. Yeah. So
Yeah.
Well, I guess, or maybe you have to do, you can just call simple after by cell.
Oh, yeah. We would have to call simple to evaluate the bell. Oh. Bell is defined how I'm expecting it to be, right? Yeah. Yeah, okay. Well,
I would just unfold it. This does explicitly call unfold bell before simple.
okay. The scalar doesn't seem to be progressing at all is the thing.
What happens if you do LCA now?
We can try LCA, yeah. And it doesn't seem to work.
And you would need C field, but I think there's still a few things that's not that fault in the issue.
Okay.
You can see for just the nice one.
Yeah.
Yeah.
Because LCA doesn't understand square roots because it's not, it's just a field tactic.
Do I need to hand C field some extra square root related things, maybe?
Yeah, that's
No,
what
because it has that built in. I think it's just a matter of, it looks like it's not unfolding everything because it's not, I'm not actually seeing an equation here. I'm just seeing something over, right?
It doesn't substitute.
It hasn't replaced it hasn't, replaced the 1 with its actual value there. So,
Right.
there's a database there's an unfolded database that maybe, I'm not sure if it's been generated yet.
There is an auto unfold with UDB.
All right. Ha! Look at that.
Right, okay. And then that should be solved. That looks like C field has solved that.
No, I think this.
I'm just gonna, okay. Yeah, okay, so C field simplify gets us to this point, right? And then these twos it's having trouble with.
LCA should work now, right?
Or these are LCA. Yep, okay,
You need to field simplify just to get rid of this code.
yeah. Just do that. Okay, yes, the C field simplify is necessary because of the square roots. The auto unfold should be able to, no, it shouldn't handle bell, I don't think. Have we put that in there? I'm gonna try that real quick. Okay, yes, the bell isn't in the UDB, but the UDB, it's on our cheat sheet. It unfolds matrix and quantum expressions for us. Right, and so yeah, we can prove that the bell state is actually equivalent to this specific quantum state that we can provide. Okay, so we can talk about measurement on quantum states as well, total and partial measurement. and we have sort of a quick recap. But this is the same thing that we saw before, right? But now we're using some different language. We have C norm 2 here, but all it is saying, if you can turn this this qubit phi into this simplification, then this part of the simplification, norm squared, tells you the likelihood it'll collapse to this, and this tells you the likelihood it'll collapse to this. Now total measurement. Ends up extending this idea, right? We're saying, okay, well, what's the property, or what's the likelihood that this collapses to 0, 0? Well, all we need to do is look at the decomposition of it, look at the alpha, and then the norm squared of the alpha will tell us the chances that phi here will collapse to 0, 0. It's the same state we were making before, but we're instead relying on this decomposition, whereas before we were just looking at the specific value in a certain spot. Right, and so we can talk about the total measurement, the likelihood that the plus minus state measures to be 0, 1, right, ends up being 1 over 4. And so first guesses at how we're going to approach this. Probably want to unfold measure total. Or yeah, construct.
So we can try applying the constructor that we want there and just see what happens.
Yeah.
So we get a minor error, which is that we don't have a square in our.
Oh, yeah. So we don't have a square here, and so this doesn't work. But we could. Let's see if there's something for over 4.
I think you can just create a hypothesis. Yeah.
Yeah, we could also just do a replace. Over 2 squared. Square root. No, it's squared. I'm so sorry.
But you are going to have to say C norm because that's what it wants to C norm.
C norm 2 of this. Has type. Okay, and this
Are they supposed to be brackets?
brackets around this.
Like C norm is a function.
Yeah, you're just saying put parentheses around the
around this.
You might need to cast that to an R, so I'm not sure if it knows that it's a real. Okay, yes.
Well, is it able to do this with any of these? No. Okay, but that's sort of that's what we want to do, and now we can apply the measure.
Yeah, this is not LRA. It's division rate. LRA can't solve this.
Oh, right. Yeah, so we would need by field. Okay, so it's not able. We'll get to that later, I guess. Yeah. So
make it an assumption.
Yeah. Right. So yeah, now we can apply the measure that we want, but we end up getting another error, which is it doesn't know what the other thing should be. Right. So we have to tell it, well, what's the other parts of this quantum state, right? What is the alpha and delta and everything. Let's see. The alpha is. It's all just C norm 2, isn't it? Or this, right? Those are all the same, right? Oh, we're measuring a specific state. I didn't need so many of these. Okay, I'm gonna just go back and take a look at our solutions real
So
quick.
you just don't need to see norms, it should just be half on all of these, just because half, I mean, we can see that half is 0, 1, 2, so,
Right.
yeah.
Okay, right. And now LMA can hopefully do it for us, or LC. Yeah. Yeah, LMA does not though.
Oh, okay, there's still a
It's the
byte.
same reason.
Yeah, yeah. Maybe field simplified again.
Oh. Yeah, it's the same reason, the division. It doesn't seem to.
You have to say by cell again.
By cell again, and then C field simplify. Auto unfold with UDB, C field simplify, LCA. Hopefully he gets it. Okay.
I think it's just fairly simple somewhere, because it's just these mods things showing up. Simple.
Right, okay. Oh, except we've made a mistake, and we need some minuses, and I'm going to assume it's at these two spots.
It's just
Should be the last one, right?
the last two should be minus.
Last two should be minus. Okay, and then we do the same auto unfolding. Oh, but we missed. We missed one of them. This, maybe. No.
The second is the last.
I think the one you already initially liked correctly.
The second and the last? The second and the last doesn't actually go through because the second is the measure 0, is the 0, 1 state, right? And this is saying that it's measuring to 1/4, which means that this needs to be negative as well. There we go. Now the types are working. So there was some type confusion because the yeah, we changed this to be negative, which also solves the equation that we need. And we have to use it because the measure 0, 1 needs a negative here. And those were tied together in the program. And now we can see, yes, it's worked. We can try auto unfolding this maybe.
Is there an active that does this thing? Like,
That solves norms.
no, because we've been using by cell, auto unfold, UDB, field simplify, LCA a lot. Like here we don't need by cell, but
Yeah, here we don't need by cell, but the auto unfold with UDB didn't do anything.
no, this what does he field simplified? Field simplified.
I think you need to unfold C norms, because I don't think I know what's
Okay.
Yeah, now.
Okay, C field still isn't working there. But it is a complex, right?
It's
Okay.
so I think they'll already might be fine.
No, let's still see that we're testing as we have to apply.
Okay, so I'm gonna just go look. We have this for a reason. Unfold C norm to L array, and then it's admitted.
No, but LRA work there, so no matter what the.
No, this is happening.
Yeah, but it wouldn't be included in the file if it was breaking that, so LRA
Yeah. Not sure what the other goal is over there, but
It's the same, right? Because first two brackets are the same.
it should be. It looks like it'll be the same. This
It's
is
the exact same.
the exact same tactics, exact same.
If you do a simple, it works.
If you do a simple, it works.
Yeah, so there's probably a simple somewhere earlier on.
Mm.
It doesn't need to be finished.
Yes. Okay. Right, so we can talk about measurement on Bell states as well, and it will work out in sort of the same manner, right, where we're providing what the measurement should be, what this qubit simplifies to. And we can even talk about partial measurement, right? So we can say, okay, well, we want to do a partial measurement of a quantum state, and let's say we're measuring. In this case, this is the measuring of the first qubit to 0. So how we encode the measurement of the first qubit to 0 is we say, okay, well, we have the quantum state. It has a decomposition. This decomposition has some probability of the first qubit measuring to be 0. And when it measures to be 0, then the chances, the quantum state ends up in an alpha chance that it will measure eventually totally to 0, 0, or beta chance that it will measure to 0, 1. Right? So we're only working with the sort of this part of the initial decomposition is what we're saying. We've narrowed in our quantum state by measuring just the first qubit. And we have this for measuring all of the qubits in this 2 quantum state to 0 or 1. Right, and so we can talk about partial measurement, right, where we can say, okay, well, we can measure partially the first qubit of this state. And what's, with probability this much, it'll come to this state. Right, and so we can do this by doing the same stuff we've done before, right? We're going by cell, auto-unfolding all these quantum matrix operations, simplifying it and taking a look at the field over the final equations that we get. Right. And we can even talk about partially measuring Bell states, right? So we can say, okay, well, we've partially measured the Bell state. It's a half chance that we end up in the 1-1 state. Right, so we can do the same stuff. And in fact, E-apply is a very useful thing for this because it'll let us kind of eagerly apply and then specify later on what we want things to be. Right, and so then we can see what we're actually, our decomposition is looking like. And then we can say, okay, well, we know that alpha for the Bell state, right, the chance that we measure to 0, 0 should be half.
Well, what's the actual alpha of the, so what's the square root of that?
Oh, okay. So it wants root 2? Oh, that's the wrong one.
Yeah, I guess they're equivalent. I think it's equivalent.
Yeah, okay. Beta.
The one you had, 1 over square root 2 rather than square root.
Okay. Right, and so for beta, that is the probability that we are actually going to measure to 0, 1, which for the Bell state we should not be getting, so that should be 0. I'm not sure what this third letter is, so I'm just gonna have to copy it. But that one should also be 0. And then we know that delta should also be 1 over square root 2. Right, and so now it's filled in the parts of the equation. We've done an eager apply, and now we no longer have to. We can do a regular apply. And it's going to work out the same way, right? We're going to do our auto unfolds with our UDB simple and C field, and then we're going to cross our fingers we have to unfold the bell. But then it works out. Right, and so here we have a real numbered operation. And hopefully it works out the same way. We can just...
Because correctness, right?
We got to use field. Right, yeah, square root of 2 being present means you're going to have to use the R field. And here we can look at it, we can see, okay, well, it's by cell again. We don't have to unfold any bells. So let's just auto unfold, simplify, and see if C field will take us all the way. And it does. Right, and so then we can continue to talk about through LMA, just looking at how matrices for gates operate on specific states. And then, yeah, there's a ton of automation built up in here, right? Using the UDB is now built up with a bunch more unfold hints for things like qubit, C naught, not C, CZ, and swap. Rewrite hints for all these matrix multiplication stuff and some quantum specific hints. And that concludes the multi-qubit section. And now we can take a look at and kind of talk about Squire, which is sort of like a small toy language built on top of this. It doesn't have measurement. It's very simple. And it's just used to construct unitary gates, right? And talk about how we can actually prove things. You're telling me. Right, so yeah, we'll open up all our scopes for everything we've defined so it can figure out what things are. So unitaries in Squire, we're representing them as gates, which, so we have just this inductive gate construction where we're going to say, okay, well, give me the natural number that I am operating on, right? That's this argument. This is an identity gate on whichever wire you specify. And then this natural number provided over here tells you how many arguments it has. In every program, when we evaluate a program, we provide how many qubits it has in the register. And then we can use our inductive commands to actually build the structure around these gates programs, right? So we have the ability to just skip a command. We can sequence commands together, and then we can take a certain gate and we can apply it to some wire. Right, and so we give some notation for sequencing. We'll have a semicolon sequence to actions. We can have skips. We can define. This would be the gate applied to Q as a command, and it just it just simplifies down to using the apply command with the I gate on the wire Q. Right, and so we tell them, okay, the argument you have is this Q, which specifies where you're operating on. And so, yeah, we have to have some way of padding these in order to actually build up these circuits overall, right? Because essentially, we need to make a 2 to the n by 2 to the n matrix, unitary matrix out of the entire thing. But we're working with these smaller matrices, so we need a way to pad them up to be size 2 to the n. And all this does is, well, it looks for the size that it's trying to make, and it says, okay, well, if we're small enough, right, if we're within the dimensions, then pad around me with some identity matrices on either side and place the unitary in the middle. But if you've overspecified, you're saying that this matrix should be operating somewhere outside of the dimensions that we want, then just return a zero matrix, right? Which should just destroy the whole circuit for you. Right, and so CNOT is kind of the first thing that uses, and this is quite a complicated version of CNOT. There's simpler ways to do this, but what this lets us do is it lets us do a CNOT between any two wires. And it uses padding to make sure everything works out correctly. And in the same way, if the dimensions aren't followed, then it will just return a zero matrix. Right, and so then we can talk about evaluation, define gate evaluation, which will take our gates that we described in the language earlier, give them the semantics, which is just a padded matrix from quantum lib. Right, so the I gate goes to the I matrix, the H gate goes to the H matrix, but padded appropriately to fit the dimensions of the unitary we are constructing. So however many wires we've specified. And then we can finally define evaluation for our command language, right, our control language. And there we just do this standard things you might expect, where skip will just give us an identity matrix. Application will do a gate eval for whatever gate you're applying at that point at the specific height. And then sequencing actions does multiplication, but it's flipped around, is important to notice. Right. All right. Yeah, and so then we can get to start talking about how we evaluate gates and what we actually get out of them. So we can say, okay, well, we know that if we evaluate a C0 gate applied once in a two-dimensional, right, 2 qubit thing, it's just going to be the C0 matrix that we would expect it to be. It's not padded in any way. Right, and so we get this, we simplify, then we do some matrix simplification, which can automatically handle these sort of identity chroniclers for us. Right, and then we say, okay, well, solve each of those equations by each cell. You do the same thing for a not C. Why did I not just write LMA? Yeah, you can. Yeah, by cell LCA it's the exact definition. Right, so yeah, then you can do the same thing for not C. So you flip these arguments and you can show that, yeah, that is exactly what we would expect. Right, you can show how C0 behaves if you're trying to evaluate it on too small of a dimension. In either case, it'll become a zero matrix. You can talk about C0 evaluated on the 0 and 1 when you have things below it, right? Very simply, it'll just be a C0 chroniclered on top of an identity. And then more complexly, and we're not going to go through either of these because they're a little hideous, you can talk about C0s being embedded. So this is just our way of saying, okay, yeah, it's behaving the way you would expect when you do evaluation. We can talk about taking these circuits and evaluating them. We can throw these into a circuit database for hint rewriting. And we can do some auto rewriting over there. And then we can say, okay, well, this is now a circuit in the Squire language, which we know should construct a Bell's state. We've proved something similar, but in the matrix representation. And now we just need to make sure that our actual language language is correct. And so how we'd want to get started with this eval Bell. Does anybody have any ideas?
I guess you have to actually compute the input well, right?
Yeah, so if we wanted to try to compute, we can see that it'll simplify, and the Hadamard will compute. This is opaque, so we would have to eval circuit on it.
Is that up?
Yeah, and then that'll just turn it into the C0 it's supposed to be. And then we can just try the same thing we've been trying before. Now it's all in matrix form. So the same tactics we used before should work, right? By cell, auto unfold with UDB and C field.
In fact, just an LMA will hopefully resolve this. I think if we even did this, right, we'd use an LMA.
Yeah. Yes, you can just use LMA.
Can you step back before the element for a second?
Yeah.
Doesn't that pretty much introduce the square root?
Yeah, but square is present in the Bell as well, so that's
or just equal?
Okay, well, we'll see the equality there, yeah.
Right, so we can substitute the LMA. And then we can add that hint in. We can say, okay, well, if you've run into a bell, if this eval pattern, then you know exactly what matrix it's going to be. There's no need to think about that anymore. And so yeah, you can get the same stuff with the CZs, which really just works out the same way. Eval a circuit to get rid of all these C naughts, and then LMA should do it. No.
It's really worked for me. I just didn't have a simple there.
You didn't have a simple and it worked?
No, I think my thing actually screwed up.
Oh.
It led it through to the but yeah, I think it's just having a little bit of, it's the same thing we have where I don't understand this.
Yeah. Okay. So there's some square roots involved, and then so we'll have to do the by cell. So it doesn't seem to be able to see.
What happens if we simplify this?
It's like, oh yeah, because that the L2M will simplify. So let's throw the simplify in earlier.
No, I think this is still R, right? I mean, R field has to occur at earlier.
I know it's LCA here. It's always it's not always C.
Right. So now we can throw that in, and then we can talk about swapping qubits. Right. Define the C naught or define a swap gate based off of C naughts. And then thanks to the automation, we can just go through, evaluate the circuit. LMA will solve that one for us, since it's all ones and zeros. Then we can talk about how swap behaves on certain states itself, right? So, and it just works out the same way. We're able to just use our automation to write down the correct statement or what we think should be correct, and then try to automate our way through it. Right, and so we can then show swap is separable using this rewrite with swap, which just turns into a matrix, and then LMA solves that for us directly. All right, so we have we have now the generic version of swap where we're going to be looking at swap operating on all these different this total quantum state and showing that it moves around these values in the exact way you might expect, where B and C get swapped and A and D remain in the same spot. Does anybody have any ideas how we might want to start this? The first thing I think is we have this.
So again,
Hmm?
to do that like circuit simplicity.
Yes, but I don't think we actually threw this in there. So we'll do the rewrite directly because that doesn't appear to be in the database. But yes, that would be. It should be in the database. But yeah, so we can exactly do just that. Next idea. LMA should probably work here. Yeah, it's all zeros and ones. Okay.
Do you have an example with a parameterized circuit?
Parameterized circuit. I don't believe we.
Don't we have teleportation?
We don't have teleportation. No.
Circuit families?
Like yeah, circuit.
So there's some simple versions of this file like power and which is just going. It's obviously copy the same circuit. We can have more general ones, but they would become more and more complex and not be stuff that you could do that.
Yeah. The only yeah, so there is a parameterized circuit that is being worked on for the textbook, but it's not complete, unfortunately. So it's not in the current version. But yeah, that is absolutely something. Like it is possible to do some proofs about parameterized circuits.
Is technically a parameterized circuit. It says run n copies of this in parallel, and then we prove that it is indeed equivalent to a large tensor product.
Yeah. Yes. So we do have. Yeah, we can take a look at this. This was reworked recently too. Yeah. So we want to talk about parallelizing.
I wanted to see inductive.
Yeah, we want to see parallelizing n circuits, which is the simplest inductive proof we can get. So okay, well, it does rely on something that is currently axiomatized, and that is hopefully convincing to you that if you eval something with dimension s of n, and that circuit is something like pair n of a Hadamard. So this is an n-dimensional circuit, but you're evaling it on n+1 dimensions. It's the same as evaling it on n dimensions and doing a Kronecker with an identity. This is the one axiom that's kind of had to slip in here.
Has it been proved later? Or
It has not been proved as of yet in the textbook.
how difficult do you estimate? Why is it? Why is it annoying?
Yeah, so we can actually take a look at this and why it's annoying. Maybe we do that after, though.
Yeah.
We can do this parameterized one. But yes, there are reasons that it's annoying, and the main reason is it's not something you can induct over easily. Right, so we want to talk about, okay, well, I should be able to say that evaluating this parallelized thing is actually the same as just doing n Kroneckers, right? And so we do this by proceeding by induction, because we now have a family that's built up recursively. The base case is fairly simple because we can just say, okay, well, this eval 0 is going to just become the identity because the par n is at 0 is just a skip. So it just becomes the 1-by-1 identity, which is of course equal to itself. All right, so now in the inductive case, things do become a bit more difficult, right? So we have this which part is this? Yes, the par n has this condition that it's checking. Or sorry, that's not the par n. What is that condition coming from? Okay, so yeah, this is kind of doing two simplifications in step. First, it takes this par n s of n, and it turns it into this sequence action here. And then it calls eval on this, and it's able to realize what that is. So you end up getting this, which is the eval running, and saying, okay, well, are my dimensions correct? And the dimensions are correct. So we say, okay, well, it absolutely is correct, and we can show that automatically with LIA. It just replaces this conditional here with true, and then evaluates us into this conditional state where we have the identities around our Hadamard. And now we kind of have a bit of a strange dimension over here, so we have to resolve that. First, we can get rid of the 0, and then n minus n will go to 0. Simplification will evaluate that for us, and m simple will get rid of the Kronecker identity on the right. So now is where we need that axiom that we took, right? Because now we have to get something that mirrors this statement here. And we've gotten this part of it, but we need the n. So we do that, it pulls out the identity for us. We have the eval n par n. We can do another m simple. And it'll actually, so this m simple is doing this distribution, right? This has the same dimension as this, and this is the same dimension as this. They're being multiplied together, so it'll just do those multiplications in their own parts of the Kronecker and combine it together. And now we can see, okay, well, we can rewrite our inductive hypothesis again, and now the two sides match by reflexivity. We have solved this circuit family property. Right, and so this is the Kronecker and mixed product is the thing that it was using. Right, and so you can even talk about doing circuit families and how they interact with each other on specific states. So we can say, okay, well, we know that this circuit family evaluated at this dimension becomes n Kroneckers of the Hadamard matrix. And then we can rewrite, I did actually need that, okay. We can rewrite this mixed product. And now we can actually do a rewrite inside of this, this n Kron. Here, we know how H operates in the zero state, and so we can finish the proof. Yes, so we can take a minute and actually look at why this is so difficult. Right, so how would we want to proceed with this? Well,
you can unfold that. So you find out the first argument is decreasing. I forgot the exact.
So unfold on eval?
Yeah, like, I mean, what is the first thing? I want to see what the first match of the value was. The first
Right.
argument, and then you say,
Okay, yeah, so let's
match C.
matches on C. So it's actually matching on this part right here.
Okay, you don't match on the.
Right.
Okay, then I guess it has to be inductive.
Inductand. Okay, and then the base case works out pretty straightforward. We can simple m simple, or simple element, I should do it. Okay.
So I have a minor objection to this statement of dilemma, which is that it looks like we're trying to prove strict equality. And I always have to prove matrix equality.
Yeah, that is, yeah. All of the tools use matrix equality anyway, so if you just go to strict equality, you lose everything. Right, so the base case is handled, but the inductive case, so the problem is, right, there is a problem, it's maybe not immediately apparent, but it comes in this. We have an inductive hypothesis that decreases a single successor case of eval down by one, but we actually need to either decrease this two case or increase this case here, and there's no way to do that with induction over n.
So if I rewrite the hypothesis on the right side,
So rewrite,
just rewrite direction.
and
So on the right matches that, doesn't it?
yeah, it does. No, it does. This is a weird thing that pops up
No,
sometimes.
it doesn't match this, but then SN.
Oh.
This mismatches that.
Yeah. The problems I've run into when I've been trying to find like a way to do this reasonably that's not like overly convoluted is this has an n in it, and also this does, and
So this okay, that's parallel and
So one thing you can do is you can replace one of the n's with, you can have an n and m and a precondition that those two things are going to be equal to one another. and then leave one of those generalized, the other one specific,
Hmm.
and that might work. I mean, there is a proof of this lemma in the
In quantum lib.
Square development.
Hmm.
So I suspect that's how we did it, but I don't remember all the details of that proof.
Okay, so we'll do SM here, and then. So this is the statement that you would recommend to do this.
In fact, you might even be able to, it might be better because equality is a bit strong. You might want to say that the number of parallels we're doing can be, as long as it's less than the dimensions, we're fine, right?
Right.
So that might actually be a more general when we get to the inductive case.
Right.
Because otherwise it would be inductive case, right? So I kind of like this level.
We have absolutely no promise that you'll be able to prove it in the next 5 minutes, but there's a next, no?
Yes, they are. Yeah, there's no guarantees this will be proved anytime soon, but this is an interesting trick, though. Right. And then we would do some induction over n this time.
Yeah, I think there's even a more general version of this one. I'm not sure why this is particular to par, and I expect that that's causing problems. We could just say that for any given circuit, provided evaluating it under, for n plus 1 wires is equivalent to evaluating it for n wires with an extra tensor I at the end, again, provided that that circuit is well formed.
Yeah, I think the reason we don't have it is there's no well-formedness property in this quite yet.
Yeah.
But that would be the way.
Right?
Yeah, it's fairly easy to say. That's the way that I would do it because we have this this target qubit here given by these nats and this nat over here, I guess. And we can look through an entire circuit and we can say, oh, well, we know which circuits are going to have a target dimension smaller than this. So we could just say, okay, well, if it is that case, then sure, we can do this. And that's something that LIA should be able to automatically solve because it's really just checking a comparison of two numbers. So in most cases, that's something that could be automated, which makes it fairly useful.
To be honest, though, I'm not, now that we've changed the dimensions and the number of cards going on, I'm not sure that this is hard. I don't know if it's worth spending much time on, but I'm not sure if this is hard.
There's some other examples to show this.
Yeah, there are some nice examples of the class.
So you're saying move on? Yeah, okay. Yeah, so we have sort of two remaining algorithms that have been built up. We have super dense and super dense coding, and then we also have Deutsch's algorithm. So going through super dense, we have an encoding stage, right, where we have two Boolean values that determine classical bits that determine if we do an X gate or a Z gate separately on the 0th wire. And the idea is that, well, we do this encoding on a bell pair, and then we have a decoding stage where we have the CNOT between the 0 and 1, and then a Hadamard, and then this decoding stage then should evaluate with the first classical bit being encoded on the first qubit, and the second classical bit being encoded on the second qubit. But we only ever interacted with the first qubit, right? And so we can get rid of that. And we can run through this proof. So introducing our Booleans. Anybody have any ideas for how we want to start this?
The night where would probably destruct B1 and B2.
Yeah.
Could you not do it in more general without specializing B1?
I don't believe so because of these statements in the in code. They make it so that if we want to actually evaluate to know which matrices we're working with, we do need actually to look at these. But right now we have this eval, and we can actually simplify it and see how far we get. Can then evaluate it with these C naughts. We know what these are supposed to look like. We can run some matrix simplification maybe. But at this point, any ideas for what might come next? I think this uses a tactic we haven't talked about, doesn't it?
There is some qubit tactic, right?
Yeah, there's another qubit tactic,
Qubits.
qubit simplify, and I believe this one uses it. To like great effect. Or it just hangs. Okay, yeah, so the qubit simplify got us to this point, right? So it went through, it did as much of the computations as it could on the qubits. And now we're still doing a matrix comparison, so
qubit simplified turns out it doesn't resolve until you look away.
yeah, you have to go to another window and come back, and then qubit simplify will be done.
And then you've observed it. then it works.
Right. So any ideas for what we might want to do next? We have this qubit simplify, which has gotten us most of the way there, but now we have run into some square roots, which often cause trouble, unfortunately.
If you expand the plus and minus the square root should disappear. What seems tedious.
It does, yeah. Yeah, we wouldn't want to expand the plus and minus because that's hopefully we have things that can help us get around that.
Like the same thing we did before the by cell followed by the.
That sounds like a good idea. We can do a by cell followed by auto unfold.
They should be named with another tactic.
Yeah, this might be a nice common tactic to wrap up. Right, but we can do this auto unfold unitary database and C field.
No, I think LCA should work at the end.
Yeah, it looks.
Now it's
Yeah, maybe we can just do. Okay, so we'll do the C field simplify, and then LCA. Okay, cool, and we can hypothesize that maybe this does work for the next one as well. Right, it sort of is the same structure. We're just solving a bunch of these linear.
It's the exact same.
Yeah.
That's
So something might change at the end here, right? Because one of our booleans has changed, so we've actually had a gate operation that we might not have had before.
10 seconds for case. So that's
But yeah, it's a couple of seconds proof, but it does end up working in the same way. There are minor differences. The minor differences come in whether or not the X gate is being applied.
You can probably stop copy pasting and just make the full stop semicolon after destruct.
Yeah.
Yep, then
Then change everything to semicolon.
no, but not only that, then we have to rerun 4 instances of eval circuit like what we had already run 304.
Yes.
You should have done that.
Maybe it'll go faster. Maybe it'll be parallel.
Yeah, I don't think anything in copy is parallel.
No, it won't be. They give you the option, though. They give you the option to specify multiple threads in a make file.
So only about 15 seconds on my computer, but
Well,
why is it so slow? It's just two qubit. Okay, that's four trust.
There you go. My laptop can boost now.
So somebody on the DST mailing list asked if there's like, if you're just doing something wrong and there's any way to speed it up, and the total node just get a 5 gigahertz. That's
Yeah, that's the speed up. The speed.
That is the solution.
Just I turned on my laptop's ability to throttle or boost, and now it's taking still 10 seconds. It's still forever. All right, so Deutsch's algorithm. So this is the very basic Deutsch's algorithm, right? So we have to find a way to encode consonant balanced, and we're only dealing with 2 bits, but we can define our Deutsch, right, for some command. We do these Hadamars and then do the UF and then Hadamard on 0. And we say, okay, well, some unitary command, some our oracle it's constant if it has a structure like this where we skip, or a structure like this where or is that? No, sorry, structure like what? That doesn't. Oh, yeah, with an X gate, so it'll be it won't actually change. And then balanced F2, F3, right? So we have a C naught beforehand. That's sort of the restrictions we have to put in to say, oh, how can we encode this constant or balanced? Right, and so how this one goes is we have this constant thing. So we're showing that it's correct on the constants. So given some constant thing, Deutsch should evaluate to this, and we destruct the constant to get our two different gates. They're F0 and F1. And right, we introduce some new variables. We say that, yes, that new variable is the qubit that we are going to have at the end. And we do some simplification. What's happening here with the specialize? It's doing...
This is the first index to the matrix D1.
That's what I thought, but is that what's happening? Oh, sorry. Okay, yeah. So this is an equality thing that we kind of skipped over. It's circuit equality, and it's defined up here. I think it's actually this congruence, right? So we're saying that 2 commands are in our language are equivalent if for all dimensions the eval at that dimension is equal to eval at the other dimension. Right, and so that's why we're doing the specialize here with 2, is we're saying, okay, well, the specialize is a dimension that we're evaluating at to 2. And then we can use it in our rewrites to change the UF into our F0. And qubit simplify, which will take not as long, gets us almost all the way there. We unfold this phi to expose this. This is an E exists, so it's now a whole. And then we say, okay, well, you can figure out pattern-wise what should go there.
So there's a real, not fake question, but why not just say E exists? Did something was...
I actually don't know.
No, we just have to say
Oh, yeah, you just do E exists.
And your question is, well, it accidentally instantiated to something that we don't want it to. And it looks like it is precisely that.
Yeah.
I'm wondering where it is that. Right. It's already done.
In M simple.
Oh,
So we could...
Having qubit simplify is value.
it looks again simple.
Yeah, so... Yeah.
And that's because, I guess, it's not very well guarded. It's willing to rewrite.
Yeah. That's how we
Yeah, in order to get around that, you throw in this E bar. And then the other side works quite the same.
So this this technique doesn't generalize to the Deutsch algorithm, right? Because you can't emulate all the functions.
Yeah, this is why I would. If you could find some nice.
General proof just based on the property, like, I mean, we could count the
Yeah, if I wanted to.
constant is fine, balanced is.
Yeah, but I mean, yeah. The way I would think to do Dutch Jose would have to do with sums, right? So to talk about
Yeah,
constant versus balanced, you would say that the sum is a function.
the sum is
Um,
2 pi minus 1.
Yeah, right. And that would be sort of the way that I would consider approaching that.
The proof the proof technique has to be completely different, right? Because the property you have at hand is just completely different.
Yeah. This is a much simpler property which serves as a nicer exercise than something like the full Dutch Jose might.
Do you have, not in the book, but do you have a proof for Deutsch Jose that I just
Does Squire?
Multiple proofs of Dutch Jose, both in the Quire and Squire project. And interestingly, so the way you suggested doing it with sums exists in, I believe that's the way that Squire approaches it. But in the Quire development, Xian Hung, who is at the time at the University of Maryland and now is at the University of Texas, had this nice way of inductively constructing a arbitrary either balanced or constant oracle, and you were able to then do induction over that oracle and prove the Deutsch of the algorithm correct. So, admittedly, that like just having a sort of, you know, a summation that will sort of classify the oracle instead of inductively constructing the oracle feels a little bit more faithful to sort of how Deutsch Jose is described. So that which is really more faithful than what we have here, where we're saying, you know, the oracle is exactly C naught. It doesn't have to be exactly C naught, it just has to be semantically equivalent.
Right.
So I guess we include semantic equivalence when we talk about constant or balance.
Right.
Yeah, so there where we specify that it's got to, you know, follow this construction, we will make it either constant or balanced. It's a little bit restricting, but it went to make a pretty nice construction.
Yeah, it ends up working really well as a nice shorter exercise or walkthrough to like get some intuition.
Yeah. So the broader, you know, stuff that is built on this, or really that is built on that slightly different version of this, has everything you'd expect. Fourier transform, Grover's algorithm, Simon's algorithm, Shor's algorithm, and a fair amount of additional things that we just want to play around with. Another student decided to implement quantum money as like his own little library. So yeah, this is, and you know, this is fundamentally the framework that underlies all of it. So it really is quite scalable, but it does, you know, you have to build up the automation and the tactics to allow you to do all of this. And in particular, the Vox compiler is also built on this framework.
Yeah.
But that required a lot of, you know, thinking optimization for specific strategies. And,
Yeah.
who knows, maybe we'll get the textbook to a place where, you know, the last chapter is like a proof of Shor or a proof of compiler practices.
Yeah, there's plenty in Squire. There's plenty of, and this isn't too far off, right? If we expand the textbook, we might want to talk about measurement in a language too, and then it would just be Squire.
Oh yeah, that was a question that Anita had earlier, which is, are there density matrices? You know, what if you actually wanted to talk about, you know, a density matrix, probabilistic distribution of outcomes, and you know, that is actually the original semantics of the Quire programming language, which developed into this, part of which developed into this library, and which now uses this library. And we just use density matrices.
Yeah, there's more density matricey stuff in Squire, I think, than there is unitary stuff.
I'm not sure about that, but yeah, there's certainly we use both. It's not pretty expensive.
The proof length gets a lot longer for some of these things with density matrices.
Yeah.
It's longer.
It gets longer.
For these kind of
For-
questions, right?
Yeah, for which one was it? There was quantum teleportation in the unitary sense, because you're delaying measurement. It really took, I think, in Squire official, it's like 30 lines. I don't know, but the other one is it's at least triple that.
It's
with
not more
density.
lines, it's just that it hits, so there's one really easy for quantum teleportation, which is compute. The problem, as you may have seen, is that our computation facilities are not great. So even multiplying out a whole bunch of 8x8 matrices, which is what explicit, computational proof of teleportation would do, is bad, to put it simply.
Yeah.
But it's doable and it works. And then you have one line proof teleportation that takes forever as opposed to like a 15 line proof or 20, whatever it was, line proof that is fast and readable, but is 15 lines.
Yeah.
Honestly, that's the better one, the 15 liner.
Yeah. The Squire is public, right?
Yeah.
Yeah. So
All this stuff we downloaded and played with.
yeah, all this and the actual implementation in Quantum Lib, there's slight differences, but yeah, they can all be downloaded, played with. There's examples of more algorithms in full Squire with measurement. I think that they might be even in their own files. I think they're off like to the side in an example file. So they're fairly easy to find. Yeah, thank you guys for coming and participating.